So this limit has the type 1 to the power infinity. If we let x go to infinity, we're going to end up with this base being equal to 1. So this is going to be 0, so we get 1, and the power is going to be infinite. Okay, so this is a 1 to the power infinity type. We're going to need to bring down the power with a log to be able to do this. So we set this up in this way. We let y equal 1 plus r over x to the power x. Okay, and then we're going to do log y is equal to x log 1 plus r to the x. Okay, so this allows us to bring the log down. As we do a limit, we're going to end up with essentially infinity times log 1, which is 0. So infinity times 0. So I'm going to rearrange this and do a limit. So we're going to do the limit as x goes to infinity. Okay, this will be log 1 plus r over x all over 1 over x. Okay, so now we have established our condition here, because if we plug in, we have our 0 over 0 condition. This is equal to 0. Okay, this is going to be equal to 0 when we let the x go to infinity. So we have our 0 over 0 condition, so now we can apply L'Hopital's. So applying L'Hopital's, it's going to look like this. So this is applying L'Hopital's. So I'm going to differentiate the top and the bottom independently of each other. And that's the idea behind L'Hopital's rule. So differentiating the top, I'm going to end up with 1 over 1 plus r over x. And then I have to apply chain rule. The derivative of r over x is negative r over x squared. Okay. And then the denominator, when I differentiate the denominator, I'm going to end up with negative 1 over x squared. Okay, so then I can cancel out those x squareds, and I end up with this expression, which I think I can substitute in at this point. Yeah, it looks like I can. So I'm just going to clean this up. So those negatives cancel out, the x squareds cancel out. So I'll show that algebraically here. These x squareds cancel out, the negatives cancel out. So I end up with r over 1 plus r over x. Okay, so this becomes the limit as x goes to infinity of r over 1 plus r over x. Okay, and then I can now substitute the infinity, so I end up with r over 1 plus 0, so that basically becomes r. Now what we've established then is that log y equals r, so then solving that, we need to just make sure we actually get the y. So since log y equals r, I can say that the y is equal to e to the r, okay, and therefore this limit is equal to e to the r. Okay, and this is actually the limit for the exponential growth formula, and this is why, if you take a look at it, this is if we increase the number of compounds and the number of times we compound it, and as we do this infinitely, we get continuous, what we call continuous growth, and continuous growth will give us this E formula, and essentially that's our interest rate here, okay, and that's going to be expressed as e to the r. All right, take a look at this one here, where this one ends up being an infinity minus infinity type. So what we're going to have to do is set up some sort of ratio to do this. So we're just going to get a common denominator here and put it into and see what the ratio looks like. So let's take a look here. So we're going to go limit as x goes to 1 from the positive side. This is going to end up being x minus 1 minus log x. That's all over the common denominator of log x times x minus 1. Okay, so there we go. So when I plug that in, I'm going to end up with 1 minus log 1, which is 0. And then I end up with log x is 0 times 0. Okay, so I end up with 0 over 0. So here I have my condition. I now have my condition to apply L'Hopital's rule. Okay, so there's my 0 over 0. As long as I have that, I can apply L'Hopital's. Okay, so that's what I'm going to do. I'm going to apply L'Hopital's here. Okay, so this ends up being the limit as x goes to 1 from the positive side. Okay, so this ends up being 1 minus 0 minus 1 over x. Again, remember that you're just differentiating the numerator and denominator independently. The denominator, though, however, is a product, so we have to apply product rule here. So we end up with 1 over x times x minus 1 plus log x times the derivative of x, which is 1. So I'm just going to leave that as log x. Okay, so I'm just going to simplify this expression. So I'm going to multiply the top and bottom by x to get rid of that divide by x. Okay, so I'm going to end up with limit as x goes to 1 from the positive side. This ends up being x minus 1 on top. I end up with x minus 1 plus x log x. Okay, so plugging in then, I'm going to end up with 0 on top, and I end up with 0 plus 1 times 0, so I still have this 0 over 0 term. Okay, so this is still equal to 0 over 0. Okay, well that's a bit of a bummer, but really it's not bad because I can actually reapply L'Hopital's again. So I can do L'Hopital's one more time because I have the condition again to do L'Hopital's, and I can just repeatedly do L'Hopital's. So that's what I'm going to do here. So I'm going to apply L'Hopital's, and I have the condition to be able to do that. And I'm going to differentiate this again. So I'm going to end up with a limit as x goes to 1 from the positive side. The numerator just becomes 1. Okay, the denominator is 1 minus 0. Here I have to use product rule. So I end up with log x plus x times the derivative of log x is 1 over x. That's all in the denominator. I should simplify that. So that becomes 1. 1 minus 0 plus log of 1 is 0. And then that's going to be 1 times 1 over 1. So that's just 1. So I end up with 1 plus 1. So I end up with 1 over 2. Okay, I have no more x's in this expression. Oh, sorry, I do have x's in this expression. Let me just do that properly here. So I'm going to end up with 1 plus 2. Sorry, so that's going to be 1 plus 1. I'm going to make that into 2 plus log x. When I apply the limit now, when I put the 1 in, I end up with 1 over 2 plus 0, or 1 over 2. So that ends up being the limit of that particular problem there. Okay, and again, we can graph all these and just check. So if you're not sure if you've done this correctly, make sure you graph. The easiest way you can do limits is by graphing. So there's probably no answer keys for a lot of these. But what you can still do is just graph them to just check your solution, if your solution actually works. Okay, so this one here, this is a 0 to the power 0 type. Okay, and we may or may not have looked at this, but this is what's happening to this as we get 0 to the power 0. Does the base win out and become 0? Does exponent win out and become 1, right? Because exponent's going to make it go towards 1. 0 exponent is 1. 0 base is 0. So which is more powerful? So this is a power one. So again, we're going to have to put this into the log form. Okay, so if I use the log form, So let that be y. Log y ends up being x log x. Okay, and if I plug in 0, I end up with 0 times negative infinity. Okay, so I need to put this in a ratio form. So I'm going to write this as a limit. So limit as x goes to 0 from the positive side. And I'm going to write it like this. Log x. It's much easier for me to put the 1 over x into the denominator. Okay, so I end up with infinity over negative infinity. Sorry, negative infinity on top, positive infinity on bottom. We don't know what that is. Okay, so I have my condition to use L'Hopital's rule. Okay, so just going to put that in. I'll make sure that's highlighted in different colors. So this is negative infinity over positive infinity. Okay, so there's my condition. I'm going to apply L'Hopital's rule. Okay, so using L'Hopital's, I'm going to end up with the limit as x goes to 0 from the positive side. The derivative of log is 1 over x over negative 1 over x squared. Okay, so this simplifies to just x, or negative x in this case. Okay, so I end up with negative x in the numerator. So when I plug that in, I get 0. So there's the limit of the log. Now remember that I've only solved for the log y. So I still need to find out the y value. So I think I have space down here, which I'll write it. Okay, so this log y equals 0, then I can say that y is equal to e to the power 0. That means that y is equal to 1. Okay, so there's my limit. When as x to the power x approaches 0, 0 to the power 0 essentially is 1. Okay, because it's tending towards 1. So what ends up happening here is the exponent, or the power, is more powerful than the base, and that's probably why they call it the power.